Good morning, everyone. Thank you all for tuning in. I hope you are all well. First of all, I'd like to thank the organizers for giving me this opportunity to speak to you all and overall for the time they've dedicated to making this conference happen, especially in these unusual and challenging times. This morning, I thought I would share with you our application of metal forming to manufacturing sheets of nanolayered materials. This work would not have been possible without the efforts of several students and colleagues, and I hope and plan to acknowledge their efforts through this talk. And not least, none of this would have been possible without the support of our sponsors, so we are very thankful for their investment in fundamental work. One of the premier attributes of metals is their ability to be reshaped and to still maintain high strength afterwards. In the rolling process, for instance, to produce sheet material, the metal experiences substantial amounts of strain. Externally, we witness a shape change, this reduction in thickness, this elongation in the rolling direction. But internally, there are also significant alterations. The grains making up this metal, they change their shape, they incur large changes in crystallographic orientation, or what we call texture. And inside of each grain, there's evidence of action of numerous dislocations. And while individual dislocations are on the atomic size, thousands of dislocations are responsible, as you can see, for the displacement of just one of these grains. And in fact, in just one of these slip traces and just one grain, thousands of dislocations in their glide action are responsible for this deformation. So when we think about severe plastic strains, such as those that are incurred in rolling, we need not account for every single dislocation, but we think of their action as collectively as slip. So metals have many outstanding qualities. One of their downfalls, however, is that they are dense, they are heavy. So there's been an age-old, long-standing initiative to make them stronger, and so less metal can be used. So it's no surprise that we do not use pure metals. Instead, we invoke numerous ways to strengthen metals. Most metals involve making most of these methods make it more difficult for dislocations to move. That's usually the key idea. From alloying to forming nanoscale precipitates and strain hardening and introducing particles, for instance, within the grains, and of course also grain boundaries where arrays of dislocations can be stopped. So grain refinement, reducing the average size of the grains and increasing the fraction of grain boundaries, which hinder dislocation motion. Those are common methods to strengthening a metal. So one effort towards strengthening has been to form the ultimate strengthener, I would say, the ultimate blocker to dislocation motion, which are walls of these bimetal interfaces. So nanolayer composites are comprised of such blockers or walls. They are formally defined as consisting of two dissimilar metals stacked in alternating layers and arranged in this 2D architecture. The individual layers are just a few nanometers or tens of nanometers in thickness, as you can see here. Some examples are copper niobium, magnesium niobium, or zirconium niobium, and then even here I got copper tungsten. So note in all these examples, they are comprised of pure metals, and the spacing between the adjacent interfaces is again on the order of nanometers or a few nanometers. So the bimetallic interfaces become the main obstacles to dislocation motion in these nanolayered composites. And with such a fine spacing, they do have then just large density of bimetal interfaces. So there are more interfaces than they are grain boundaries, and they're also comparable to just the amount of crystal in the material. So you may notice that despite these very fine nanometer layer dimensions, that the layer morphologies are highly regular. They have a uniform layer thickness, very well controlled periodicity. And this is possible because these nanolayer composites have been deposited. They were built from bottom up, atom to atom, if you will. These samples overall are thin. They come as about several hundreds or a few hundreds of microns thick, or tens of microns thick, I'd like to say. And if these two metals are immiscible, which they usually are in these kind of composites, that you can obtain interfaces that are pristine, that even at the atomic scale in these high-res TM images, you can see here that that these interfaces are sharp and quite and quite perfect. So also the crystallographic orientations here are not distributed there, but they're highly oriented. And they're chosen specifically so they could create the mutual interfaces between the two adjoining crystals so that so that the interfaces themselves are low in energy. Now, so the question is, are these nanolayered foils strong? I mean, that's ultimately was the purpose for creating them. And so we find that they are very much so strong. For these magnesium niobium nanolayer composites, for instance, when the individual layer thicknesses range from about 50 to 2 nanometers, the hardnesses range anywhere from 2 to 5 GPa. Similarly, for the copper niobium composites, for layer thicknesses ranging from also 50 nanometers down to 5 nanometers. Again, this is just the individual layers. The hardnesses, again, we're measuring hardness, ranges anywhere from 2 to 6 GPa. And this likewise for the zirconium niobium nanolayer composites as well. So in all these cases, you notice that at least for these, we're reporting hardness. This was a converted hardness to flow stress, that these were obtained from nano indentation calculations. And so also these measurements do show that these nanolayer composites are 2 to 10 times stronger than the strength of or the hardness of any of these individual metals that one would obtain. Also, if you were just to do a volume average calculation of their strengths, still the hardness values here are close to an order of magnitude higher than you would have from this volume average calculation. So the volume average calculation for strength does not account for the interface. And so these ultra high hardnesses are what we refer to signs as interface dominance, that because they are unexpectedly and they high and they exceed that of a rule of mixtures type calculation. So then the question had become, what exactly are the interfaces dominating? They dominate the strength, but how? And so for plasticity and metals, the main concern then becomes the effect of the interface on dislocation motion. So since these nanolayer thicknesses are on the order of maybe 1 order of magnitude higher than the dislocation size or width themselves, which is usually 1 nanometer, that now the interface dominates over the motion of that dislocation. In fact, the entire life of the dislocation. So when and where it will be born, when and where it glides, and how it ultimately terminates. So then it becomes important to resolve an individual dislocation, to track how it's moving. And so these these remarkable strengths of the nanolayer composites renewed interest in resolving the interactions of just single dislocations and with interfaces under a mechanical deformation. So this called for molecular dynamics simulations, or these are atomic scale simulations. Many of these works here that you see were carried out to elucidate mechanisms or resistance to motion of nucleation, the resistance to threading through these layers, the resistance to transmission across these layers, and also how well do these interfaces block even in extreme strains. And also, more importantly, the ability for these interfaces to heal, to actually annihilate and act as sinks for these interfaces. So they all, in these calculations, all found them to be unusual and fascinating, and how profoundly the interfaces control dislocation motion. Now, this achievement of interface dominance over strength of these nanolayers were made possible in these deposited nanolayer composite foils. How they were strength tested usually involved nanodentation, as I mentioned, but also micropillar compression because the size was limited. Now, yet there are many mechanical testing techniques and characterization techniques commonly involved in studying high performance metals that we were accustomed to using in our studies, but we could not use here due to their small, fine size. And then, of course, another perhaps glaring limitation arises from a technical point of view, that one of the significances of strong, better metals in part relies on their use in structures, and one cannot make structures from foils. So for some time, there's been a parallel effort to make nanostructured two-phase metals from metal forming, or in particular, severe plastic deformation methods. So these methods, severe plastic deformation, or SPD methods, they can impart extreme amounts of plastic strain while retaining the individual or the original dimensions of the sample. And so I have a few examples here. Back in the late 90s, equal channel angular pressing, or ECAP, was applied to a two-phase composite, or metals such as copper niobium or copper silver that I show here. Another SPD method is wire drawing and bundling. And with this, it is possible to make standard size copper niobium wire, but ones that are internally nanostructured. Here in this example, the copper niobium are on the order of 20 nanometers in thickness individually. Now, also about over 20 years ago, cumulative roll bonding, or ARB, was applied to deposited iron silver foils. And so these foils were then stacked and rolled, and then their layer thicknesses were reduced from tens of microns down to about 2 nanometers. So pretty outstanding. So something I want you to notice is that in all of these examples that pure metals were used. So these, in the pairing of the metals, were intentionally chosen that they were immiscible, and so they did not mix. And then also something to note here is that these pure metals, and they're in this form, they are all soft, so that they could be severely plastically deformed at room temperature. So then we asked the question, can we apply this SPD method to standard sheet material and manufacture nanolayer composites? And so for our studies, from a scientific viewpoint, we wanted to obtain nanolayered materials, but in sheets, so it would enable us to use standard characterization techniques and also testing techniques, so that we could access more than just hardness or pillar strengths. And then, of course, from a technical viewpoint, ultimately, manufacturing stock sheet material would pave the way to making actual structures. So this is what we did. We applied the cumulative roll bonding, ARB, if you will, process to 50% of copper and niobium. So we did start with separate sheets of copper and niobium, about millimeters thick. And so how this works is that you stack these sheets in an alternating sequence, and then roll them and roll bond them, if you will. So that means that once they're stacked, you roll them, and then they come out bonded and then also elongated. So as they're elongated, you would cut along that length, then restack again, and then repeat the process of roll again. So that is considered one ARB pass. So for the first stacking and each restacking, we did clean the surfaces, and they were wire brushed to aid in the bonding. But also one important point is that these stacks were what we call copper cladded. So that means that the bottom and top sheets of the stack were both copper, and the copper were half thicknesses compared to the other sheets in between. And so the reason this was done was to not expose any of the interfaces to air. So what's going to be exposed is some internal part of copper. And also, as we create interfaces, as you will see in the next slide, by this roll bonding process, that none of these interfaces are created by the restacking. You only restack copper to copper. You don't restack copper to niobium. So all the interfaces, once they are cladded inside, they are all formed, and none of them are exposed to air. So here I'm showing you the evolution of layer thicknesses with every ARB pass that we started again with this copper cladded stack. Rather thick sheets have been stacked. And so with every ARB pass, we reduced the layer thicknesses rather uniformly, I would say. And another way I like to think of this is that we are creating interfaces as well. So we're creating interfaces where we're refining the individual layer thickness. And so, and we got down, I would say after about 7 passes here, that the layers then turned out to be less than 100 microns. And at this point, you probably can't even make out the individual layers so easily. So at the end of every ARB pass, we have sheet material. And at any point in this process, after any number of ARB passes, we can test the sheet material. We can create dog bone specimens. We can also create cylinders or cubes for compression testing, perform creep tests, even flyer plate tests for shock compression. And then also this shows here kind of a funny thing where the student was pretty excited after creating this first nanostructured sheet that he took it out to the shooting range that weekend and just shot at it. And so actually some interesting things came out of that. So more on that later. But you know, another thing I mentioned, we could also perform standard characterization techniques on this material, such as in situ digital image correlation, DIC, to study instabilities, and neutron diffraction for non-destructive texture measurements, and then on a more destructive aspect, EBSD for just local microstructure and orientation mapping. So let's look at what happens after 7 passes. So after 7 passes, over thousands of percent strain, the individual layer thicknesses have now reduced down to below 100 microns. They still are distinct layers, and then within every layer here, we still have multiple grains spanning the layer. For instance, in this case where we have this individual layer thickness is 45 microns, we can make out grain sizes that are ultra fine scale, 600 nanometers or so. A polycrystalline layers, if you will. So we have grain refinement accompanying the layer refinement. And this texture, as far as textures, these are neutron diffraction measurements. This is a common measurement that we obtained within this layer thickness range. And still, we see that if you are familiar with looking at textures for BCC materials and FCC materials, you will recognize right away that these this distribution orientations or textures from these pole figures, they are as they would be expected from rolling the materials alone. So the phase textures represent that of the metal or pure metal or elemental metal textures. So everything is familiar here. Nothing surprising as far as microstructure. So in principle, we can keep going. We can apply more ARB passes from 8 to 10, and we can thereby impose more strain. And in doing so, we continue to refine the layers further and increase that area of bimetal interface. And so we were able to refine the layers from down to submicron levels, down to 30 nanometers, even down to 10 nanometers. And so at 200 nanometer layer thicknesses, you can see that from this EBSD image that now the layers they're still distinct. We still have distinct copper and niobium layers. The compared to the deposited copper and niobium, they're not as pretty, I would say. They're not as perfectly and morphologically planar. But when we work with metal forming, our goal really is to refine the layers and keep them distinct. And it was not so much to control their individual morphology. As we now start to dive down into submicron levels, 30 nanometer layer thicknesses, and 10, we're right at the edge of orientation mapping by EBSD, and we now start to use TM to make them out and to study their nanostructured characteristics. In this case here with the EBSD, we can see that now in this layer thickness range, we have a single crystal spanning the individual layers. And so what that means is that each copper crystal is joined to two neighboring niobium crystals. So we have mostly biphase interfaces here. And so also we find that at these unusually fine thicknesses that it's very hard to make out any grain boundaries actually. So there's very few grain boundaries. So we truly have a bimetal interface dominant material. So of course now the question is, what's the strength of this stuff? So what we did was we had taken sheets of this material after different numbers of passes, which corresponds to different layer thicknesses, and all in this fine range of layer thicknesses from 1.8 microns down to 15 nanometers. And here I've shown here dog bone tensile tests that were taken, and these dog bones were cut in the both in the rolling direction and also along the transverse direction. So we find here that the strengths in short are very high, ranging from 400 or over 400 megapascals for the 1.8 micron layer thickness down to about 1.2 GPa for the 30 nanometer case. Similarly for the compression response as well, we're exceeding or getting close to 1.2 GPa for the 30 nanometer nanolayered material. In all these cases, the yield strengths, the ultimate strengths are 5 to 10 times the strength of just that of copper or niobium alone, and also much greater than if we were just to take the volume average strength of this 50-50 mix of copper and niobium. So, so definitely we're witnessing clear signatures of interface dominance here. And so, oops, sorry. Oh, a little slow. So now in this slide here, we are taking a closer look at the tensile data. Here, the yield strengths are plotted on a Hall patch plot, but rather than layer thickness, rather than the grain size, we're considering layer thickness. So yield strength is plotted versus the inverse square root of layer thickness. And as shown here, that a linear relationship emerges, which indicates that the strength and the layer thickness follow this empirical Hall-Petch law, which was originally surmised for pure metals and for in relationship to their grain size. So we did this analysis individually for the transverse direction and the rolling direction. In both cases, they seem to follow this Hall-Petch law. So finer is stronger. So finer layer thicknesses are stronger. Now, the main difference here, though, is that these strengths we don't see any softening in the yield stress as we get finer, and certainly that these strengths are, again, outstanding compared to what you would expect for pure copper or pure niobium. So then next, we analyze this nanostructure itself. It is interface dominant. We've established that. We wanted to examine other aspects of the nanostructure to see if there's anything still, if we retain this familiar structure that we would expect from rolling. So first, as I mentioned, the nanolayers are spanned by one grain, and anytime we have 200 nanometers and below, so just one grain is spanning this layer, so they are interface dominant physically. Also, we analyze the texture development. So again, here I'm plotting here the measurements for a typical FCC. In this case was copper, in this case was niobium, but we found that these textures that we get when we just roll the material, this is coarse grain material, just showing you this as a reference, the textures we would expect from a material that's copper, high stacking fall energy, also a typical texture we would get from a refractory BCC material. So, so here these, I don't know if you're used to looking at these pole figures, but one would recognize these as being familiar to these materials. Also, something I'd like to point out is that there is a distribution of rolling texture components. There are many of them that are considered stable when you roll the material. So something we found interesting when we compared that to use the pole figures representing the textures for the ultrafine or the nanolayered materials, copper and niobium, that we see that they are distinct. And these are the types of textures that we would get when the layers are spanned just by one single crystal each. And so first thing we notice is that their features are distinct, but the actual components that are distributed here are, there's very few actually. So very few components are found here. So, but some of them do overlap with those that would be commonly expected or considered as rolling texture components that are stable in a conventional rolling texture. So that these ARB nanolayer texture components make up an exclusive subset of those expected from rolling copper or niobium alone. And in fact, it was just a few. So another odd microstructural feature was the in-plane length of these grains inside the layers. They were it's exceptionally large. That's what I wanted to say. Normally in roll materials, the grains do become elongated in the rolling direction. We expect that. But the aspect ratios are commonly 10 to 20. In these ARB nanolayer materials, they were nearly 80 to 100 aspect ratio. So essentially, and also as we can visibly see here, these layers are single crystal sheets. And another way to look at it is that there are fewer grain boundaries than there are bimetal interfaces. So truly bimetal interface dominant, few grain boundaries. And so even in this unusually wide field of view for TM, we don't see any grain boundaries, or very few. So thinking back to these deposited nanolayers, we recall that these interfaces in those deposited nanolayers were low energy, and they were pristine even at the atomic scale. So then we ask, can we expect the same level of perfection from interfaces that are formed by rolling, especially after thousands of percent rolling strain? So we actually didn't expect that. We didn't even need or want it, but we were just curious what it would be like. And to our surprise, we found that these interfaces are rather regular and periodic, which we would not have expected because of all the interactions with dislocations that would have been involved. So these type of high resolution TM imaging was done in several parts of the material, and every time we found that they had this regular topology, and they were actually also rather sharp. So knowing the orientations of these crystals that are being joined, and there are actually just two, in fact, that we could create a 3D atomistic model of this particular copper niobium orientations. And so we create this, then we relax them, and then we calculate the interface energy and its equilibrium state, and also its structure. So what we find is that the sawtooth morphology here can be expected due to the natural topology of these planes that are being joined. So these materials, just a raw cut of these crystallographic planes, they are atomically jagged periodically. But when you join them and you then create the interface, you do create a network of these, what we call misfit dislocations, that help glue them together without free surface. And also we can calculate the energy of these interfaces. And so with this, we found that they do have this value of interface energy. It's fine. But then we wanted to test for the stability. And to establish that, what we do then is create slight deviations in the crystallography, and we recalculate the interface energy. And we find that when you do that, the interface energy rises. So any deviation from the interface that we see here in the nanolayer composites will cause a rise in energy. So what that means is that these interfaces that are found in the ARB nanolayer composites lie in an energy well. So they're stable. So there must be some driving force to create this preferred interface. So now, establishing that we have low energy interfaces in this material, it would suggest that that this material would have some stability to elevated temperatures. So we exposed these rolled nanolayered materials to temperatures that were far above the room temperature that was used in the rolling process. And so these elevated temperature tests range anywhere from 100 degrees C to 700 degrees C. We exposed them to each temperature for 1 hour, and then we tested its hardness. And we also analyzed its nanostructure afterwards. And we find that up to 500 degrees C, this nanostructure is maintained. So it maintains this layer thickness, in this case, 10 nanometers. It's maintained even after 500 degrees C exposure for 1 hour. And also the post-temperature hardness did not change. So if we just take this percentage of a decrement in hardness before and after the exposure, we find very little change. So amazingly stable. Now, if we compare that to the deposited material, we find that it is actually more outstanding in thermal stability than the deposited materials. So this was unexpected, considering that the deposit materials do have interfaces that are even lower in energy. So more on that later of what happened here, but thermally stable. So we also then, earlier, those were hardness tests or post anneal hardness tests. With these nanolayered sheets, we can now test for their performance after exposure to temperature. So we separately ran some tensile tests for these nanolayered sheets after temperatures ranging from 400 degrees C up to 1,000 degrees C. So dangerously close to the melting temperature of copper. So up to about 500 degrees C, there's absolutely no sign of exposure to thermal temperature, except maybe a few areas of pinch off. And even after 600 degrees C, we still maintain on average the layer thicknesses, but we see more regions of pinch off. And so then finally about 700 degrees C, we see visible coarsening. But what happens, we learn from this, is that the pinch off regions are where the grain boundaries are within the layers. And it's not the biphase interfaces that become unstable. So then when we test for the strengths of this material after exposure, we find at 500 degrees C, even after 600 degrees C, there's very little change in the tensile strength in tensile test response. So thermally stable. And so just by the way, that copper, one of the constituents here, 50% of the constituents, the melting temperature is slightly above 1,000 degrees C. And we also know that about 50 degrees C, copper alone will get soft. So the fact that it maintains this type of strength up to 500 is outstanding. So going along with the idea that the grain boundaries are these weak points, we then tested this by changing the rolling schedule. So up till now, all these materials were longitudinally rolled. And so we also then changed the rolling schedule to cross roll in the few last steps in order to change the morphology of the grains within the layers. And so with cross rolling, we created pancreate grains and we increased the internal grain boundary density. And we find that in repeating this thermal test, that the hardness goes down, but also thermal stability also increases as well when we when we reduce the grain boundary density within the layers. So just finally, I wanted to just go through some of the performances of these interfaces. Clearly, they are thermally stable compared to copper niobium, and also they're stable with respect to rolling as well, as they arose from as a child of the extreme rolling deformation. So naturally, we questioned their stability to other types of mechanical deformation, such as compression parallel and normal to the layers. So here in micropillar compression, we found that the failure, the way it failed was non-catastrophic, and distributed shear bands formed and they crossed the layers. they did not ever coordinate. So the failure and the softening occurred just from this light non-catastrophic pattern. And then if we look within the layers, we find that for the most part that these, or look within the shear bands themselves, that the interfaces remained intact and they remain bonded. Also, just returning back to that time when we took this material out to the shooting range, what we found surprising is that instead of failing by debonding at these interfaces, that the material created what we call kink bands. So kink bands are a common instability in fiber composites. So rarely is it found in a metal or metal based material. But when looking within these kink bands, we find that at the kink band boundaries and also within the kink bands themselves, that the interfaces and the layers remain intact, and so failure and cracking do not occur there. So we did perform a more controlled flyer plate tests, which are designed to study response under shock compression. And at these velocities that would normally cause highly defective copper or highly defective niobium, we find that despite this exposure to shock here, that the interfaces all remained intact. And so at higher velocities, higher than what we would impose on just copper and niobium alone, that we do see voids forming, but the voids all formed within the copper and not in the niobium and not at the interfaces. So as a final example, interfaces and grain boundaries are known to be sinks for defects, particularly those defects that form when exposed to radiation. And so radiation defects like vacancies are drawn to grain boundaries, and if grain boundaries then become saturated with these vacancies, they form voids. So in applying the same type of exposure to these nanolayer composites, we find that they seem to superficially to be resistant to any type of radiation damage, as opposed to an adjacent non-layered material. So if we look a little closer, we find that the damage is comprised mainly of voids that formed within the copper and not within the niobium or at the interface themselves. And in fact, the voids do occur right inside the copper, in the interior, and they are that close to the interface. There's this void denuded zone that forms. It seems to be resistant to forming any voids, even far from the interface, about 20 nanometers. So this material had 200 nanometer layer thicknesses. So the idea was that if there's a void denuded zone that's about 20 nanometers, if we made the layer thicknesses 40 nanometers or less, then under that same exposure to radiation, we would see no or very little damage. So, and in fact, that's what happens. And if there's any damage, it's in the occasional thick copper layer. So throughout this talk, I have focused mainly on the copper niobium system, but certainly this is not the only system in which ARB nanolayering has been applied or could be applied. Some similar examples are copper tantalum, zirconium niobium, and also silver nickel. So in all these cases, the reason they worked is that these metals that are being joined are formable, and they also have similar behavior at the rolling conditions. So, and they're both immiscible. So far we've used soft metals because in many of these cases, these were laboratory strength rolling mills and not industrial strength rolling mills. So this comes to the end of my talk, and so I hope you found it interesting, and thank you again for tuning in. Mainly, I hope you learn fascinated by these materials, and just wanted to in closing say that They do show signs of exceptional strength, and a lot of it's due to their rather unique interface structures. So with that, I would like to thank you for tuning in. I hope to have the opportunity to meet you all in person. And so take care, everyone.